Today, we're diving deep. We're doing a masterclass on one of the most fundamental molecules in our entire nervous system, acetylcholine. Now, what if I told you that a single molecule is responsible for everything from a simple muscle twitch to how you form a memory? Seriously, from the command that makes your body move to the very pathways of thought inside your brain, this one neurotransmitter, acetylcholine, is right at the heart of the action. So let's unravel its story.
To really truly understand acetylcholine, or AC as we'll call it, we're going to zoom in on the place it's most understood, the neuromuscular junction, or the NMJ. This is that incredibly precise point where a motor neuron connects with a muscle fiber. And it's called the ultimate synapse for a really good reason. It's not just the final link in the chain of command from your brain out to your body. Its structure is just so beautifully organized and accessible that it's become the perfect laboratory for scientists to figure out exactly how nerves talk to muscles. So, here's our game plan for this deep dive. We're going to start with the anatomy of this ultimate synapse. Then, we're going to follow the complete life story of a single acetylcholine molecule, from its creation and storage to its release and recycling, its action on the other side of the gap, and crucially, how its signal is shut down with pinpoint precision. And to wrap it all up, we'll explore the fascinating world of pharmacology, how different drugs and toxins can actually hijack this whole intricate system.
Okay, first up, let's get acquainted with the structure of the neuromuscular junction. We really need to appreciate why it's such a perfect model for all of neurobiology.
So what is it that gives the NMJ this ultimate status? Well, for starters, it's the last stop. It is the final synapse where a signal leaves the central nervous system and hits the periphery. Think of it like the final go command before the action happens. Second, the wiring here is incredibly precise. Get this, each individual muscle fiber is controlled by just one motor nerve terminal, a single one. This creates this super clean, one-to-one command system so there's absolutely no confusion. Now, the motor neuron itself, its long axon and all the muscle fibers it talks to, that whole package is known as a motor unit. And maybe most importantly, because it's located outside the brain and spinal cord, it's highly accessible. Scientists can literally see it and measure what it's doing, which gives us this unparalleled window into how a synapse actually works.
Now check this out. What's so cool about this image is how it lets us see the synapse's specialized machinery up close. Using amazing techniques like electron microscopy and something called freeze fracture, where you literally flash freeze tissue and then crack it open, we can see all the inner workings. So if you look at the top part of the diagram, the presynaptic membrane, those double rows of little particles are the active zones. These are the exact launch pads where the release is going to happen. Lined up, ready for action, are the synaptic vesicles, absolutely jam-packed with acetylcholine. Now look across that tiny gap, the synaptic cleft. The postsynaptic membrane on the muscle is just dense with particles. Those are the acetylcholine receptors, and they're concentrated in these deep folds. This whole structure, every last bit of it, is built for one thing: absolute, undeniable speed and reliability.
All right, let's move on to how this whole thing begins. We're now going to track the life of an acetylcholine molecule, starting right at its creation and its very meticulous packaging inside that nerve terminal.
Okay, making acetylcholine is this really elegant and efficient three-step process. First up, you need the main raw material, choline. It has to be brought into the nerve terminal from the fluid that's just outside the cell. A specialized protein, the choline carrier, does this job. Now, this is a really critical point. This transport process takes energy, and it is the rate-limiting step for the entire operation. What does that mean? It means the cell can only make ACH as fast as it can import choline. It's the bottleneck of the whole production line. So once the choline is inside, step 2 kicks in. An enzyme called choline acetyltransferase, or CAT for short, which is super concentrated right there in the terminal, gets to work. It takes that imported choline and combines it with another molecule called acetyl coenzyme A. And then step 3, bam, our hero molecule, acetylcholine, is formed, and coenzyme A is released as a byproduct.
So you might be wondering, where does all this essential choline come from? Well, the neuron is pretty resourceful. It has 3 main strategies. The most important one, accounting for about 30 to 50% of the supply, is recycling. It's beautiful. After ACH is used, it gets broken down, and the choline part is taken right back up to be used again. It's a wonderfully efficient system. The second source solves a really tricky problem for the brain. See, choline is a charged molecule, so it can't just pass through the blood-brain barrier. The solution? It gets cleverly packaged into a lipid called phosphatidylcholine. This lipid can get into the central nervous system, and once it's inside, it's broken down to release that precious choline. And finally, there's another cellular compound, phosphocholine, that serves as an extra reservoir.
Okay, Once acetylcholine is synthesized out in the cytoplasm, it needs to be loaded into those synaptic vesicles for storage and later for release. This is the job of the vesicular ACH transporter, or VHT. Now, this isn't just passive filling. The VHT is an energy-dependent machine that works as an antiporter. Imagine a revolving door. For one acetylcholine molecule to go in, one proton, that's an H+ ion, has to come out. This elegant exchange system allows the terminal to pack ACH into the vesicle against a really steep concentration gradient. To keep the whole thing running, special proton pumps, or ATPases, are constantly pumping H+ ions back into the vesicle, which maintains the electrochemical gradient that the VHT absolutely needs to function.
And the amount they pack inside is just staggering. Each one of these tiny vesicles contains around 5,000 molecules of acetylcholine. Now, this creates a major physics problem. ACH is positively charged, right? So cramming 5,000 positive charges into such a tiny space should cause this immense electrostatic repulsion that would just push them all apart. The biological solution here is brilliant. You just co-package the ACH with negatively charged molecules. So inside each vesicle, you'll also find ATP and these things called heparan sulfate glycan proteas. Their negative charges perfectly cancel out the positive charges of the ACH, allowing for this incredibly dense packing. Everything's ready for a powerful concentrated release.
You know, these vesicles are often built way back in the cell body, which can be a really long way from the nerve terminal. So how do they get there? They travel along this internal highway system made of microtubules, and they're powered by what we call molecular motors. When a full vesicle is moving towards the terminal, that's called anterograde transport, and it's driven by a motor protein called kinesin, which literally walks along the microtubule track. And when an empty vesicle needs to be sent back from the terminal for recycling, that's called retrograde transport, and that's driven by a different motor, diin. This whole system is a logistical marvel, just ensuring a constant supply of ready-to-fire vesicles right where they need to be.
Okay, now we're getting to the most dramatic part of the life cycle, that exact moment of release when the signal is finally sent, and the equally critical process of getting that vesicle ready to go all over again. At the very heart of neurotransmitter release is this team of proteins called the snare complex. You could think of them as the molecular machinery that literally pulls the vesicle and the cell membrane together for that kiss and run of neurotransmission. There are 4 key players in this molecular dance. On the synaptic vesicle itself, we have synaptobrevin and synaptotagmin. And then waiting on the presynaptic terminals membrane, we have SNAP25 and syntaxin. It's the precise interaction between these 4 proteins that makes release possible.
And this diagram here just brilliantly illustrates the entire release and recycling cascade. Let's walk through it nice and slow. First, the vesicle undergoes docking, where it physically makes contact with the inner plasma membrane. This is followed by a priming step, which needs ATP. And this is where those snare proteins make their first little bit of contact, getting everything poised and ready. But they can't fully bind yet. The trigger is the arrival of an action potential. That electrical signal opens up voltage-dependent calcium channels. Calcium ions then flood into the terminal. This influx of calcium is the key to everything. It causes a change in shape, allowing the snare proteins to fully bind and act like a molecular winch, pulling the vesicle and cell membranes together until they fuse. The entire contents of the vesicle, that quantum of about 5,000 ACH molecules, is instantly released into the synaptic cleft. But the process isn't over. Immediately after, proteins called clathrin assemble into a cage on the inside of the membrane, pulling that bit of vesicle membrane back in to be refilled and reused. This whole recovery process is called clathrin-mediated endocytosis, and it makes sure the terminal is ready for the very next signal.
Okay, so the acetylcholine has been released. Now let's travel across that synaptic cleft and see what happens when it binds to its receptors on the muscle fiber. So acetylcholine acts on 2 totally different families of receptors. First up, we have nicotinic receptors. These guys are ionotropic, which means the receptor is the ion channel. Think of it like a gate that opens the instant the key, which is ACH, is put in the lock. When ACH binds, that channel just snaps open, allowing sodium ions to rush in and cause a really rapid depolarization. They're incredibly fast-acting, but they only make up about 5% of all ACH receptors. The second family is the muscarinic receptors. These are metatropic or G-protein coupled, and they work much more slowly. Think of this more like a doorbell.
When you push it, it doesn't open the door directly, it sends a messenger inside the house to deliver a message. So when ACH binds here, it activates a G protein inside the cell, which then kicks off a whole cascade of downstream signals. They are the vast majority, making up about 95% of all the ACH receptors.
And even within that big muscarinic family, there's a lot more diversity. As this diagram shows, there are 5 subtypes, M1 all the way through M5. And the crucial thing to understand here is that they couple to different G proteins, which means they trigger different intracellular pathways. The M1, M3, and M5 receptors, they all couple to a G protein called GQ, which leads to one set of effects. But the M2 and M4 receptors couple to a different G protein, GI, which leads to another, often opposing, set of effects. This incredible diversity is what allows a single neurotransmitter, acetylcholine, to have such a wide range of slow, modulatory actions all throughout the body.
So let's get back to the fast action at the NMJ. This slide shows us the electrical cascade, which is just like a series of dominoes falling. When just one vesicle's worth of ACH is released, it activates over 200,000 nicotinic channels all at once. This creates a huge inward flood of positive charge, a massive current called the end-plate current, or EPC. That's the first domino. This current then rapidly depolarizes the muscle membrane, which generates what we call the end-plate potential, or EPP. That's the second domino. Now, if this EPP is large enough, and at a healthy NMJ it always is, easily exceeding the threshold of about 20 millivolts, it triggers the final domino, a full all-or-nothing muscle action potential. And that is the ultimate signal for the muscle to contract.
You know, a signal this powerful needs an equally powerful off switch. It has to be precise. So let's look at how the action of acetylcholine is brought to a swift and clean end.
The final 2 steps in the life cycle are all about termination and recycling. First, in the synaptic cleft, an enzyme called acetylcholinesterase, or ACH, works with incredible speed. It hydrolyzes acetylcholine, which means it just breaks it back down into its 2 original precursors, acetate and choline. This immediately terminates the signal. Done. Second, those components are recycled. The choline is transported back into the presynaptic terminal by that same energy-dependent choline carrier we saw way back at the beginning, ready to be made into new ACH. The acetate, meanwhile, just enters the cell's general intermediary metabolism. It is a perfectly efficient closed-loop system.
Okay, so now that we've mastered the entire life cycle, from start to finish, we can really understand how this beautiful system can be manipulated. Every single step we've just discussed is a potential target for drugs and toxins.
Let's start with drugs that mess with ACH release. If you want to enhance it, you could use potassium channel blockers like 4-aminopyridine. What they do is prolong the action potential, which keeps the calcium channels open just a little bit longer, letting more calcium in and triggering more vesicle fusion. For a much more dramatic effect, you've got alpha-latrotoxin, which comes from black widow spider venom. It binds to a receptor called latrocophilin and just forces a massive, uncontrolled dumping of all the synaptic vesicles. Now, on the other side, if you want to inhibit release, you can target a bunch of different steps. Hemicolinium blocks that choline transporter, basically starving the terminal of its raw material. Vesimicol blocks the VAHT, so vesicles can't be filled up properly, which reduces the so-called quantal size. And omega-agatoxin, from funnel web spider venom, directly blocks the P-type calcium channels, completely removing the trigger for fusion.
Some of the most potent toxins known to exist work by physically destroying the release machinery itself. Tetanus and botulinum toxins are proteases. That means they are enzymes that literally cut proteins. Tetanus toxin specifically goes after and cleaves synaptobrevin. The various botulinum toxins which cause botulism target different snares. Some cut synaptobrevin, others cut SNAP25 or syntaxin. By cutting these absolutely essential proteins, they completely block exocytosis, which causes a flaccid paralysis. It is a chillingly precise example of molecular sabotage.
We can also target the off switch, that enzyme, acetylcholinesterase. And there's a really critical distinction here between reversible and irreversible inhibitors. Reversible inhibitors, like neostigmine, just temporarily block ACH. This is clinically vital for treating myasthenia gravis, which is an autoimmune disease where the body's own antibodies attack and destroy ACH receptors. By letting the ACH hang around longer in the synapse, these drugs give the signal a boost to compensate. But irreversible inhibitors, like the nerve gas sarin, that's a completely different story. They bind permanently to ACH, completely knocking it out of commission. This causes a massive toxic buildup of acetylcholine, which leads to constant muscle activation, paralysis of the respiratory muscles, and ultimately death.
And finally, we have drugs that act directly on those postsynaptic receptors. Agonists are chemicals that mimic acetylcholine and activate the receptors themselves. They're like a master key that can open the lock. Famous examples are nicotine for nicotinic receptors and muscarine for muscarinic ones. Antagonists, on the other hand, block the receptors. They're like a key that fits in the lock but won't turn, which prevents the real key from working. Classic examples are tubocurane, which blocks nicotinic receptors, and atropine, which blocks muscarinic ones. A clinically vital antagonist is atracurium, which is a derivative of tubocurane used as a muscle relaxant in surgery. It's so valued because it spontaneously breaks down in the body, which really minimizes its side effects.
So, the crucial point here, the big takeaway, is that understanding this detailed life cycle isn't just an academic exercise. It has profound clinical applications. Because we understand the off switch, we can use ACE inhibitors to treat myasthenia gravis. Because we understand the receptors, we can use nicotinic receptor blockers as muscle relaxants in surgery. And this all goes way beyond the NMJ. Cholinergic pathways are vital in the central nervous system for things like memory and attention. When they stop working properly, they're implicated in neurodegenerative disorders like Alzheimer's and Parkinson's disease. And guess what? Those same ACE inhibitors are a mainstay of therapy for those conditions as well.
And so as we wrap up this masterclass, I'm going to leave you with a final thought. Having walked through every single step, from synthesis all the way to breakdown, and having seen all the available targets, if you could design a new drug to precisely modulate just one of these steps to treat a disease, which step would you choose, and what would be your reason why? It's a fascinating question that sits right at the very heart of modern pharmacology.